Okay, test. Tests. Okay, thank you. Good. All right, good morning. Let's get started. So we'll look at convolution through an example, which will demonstrate this so-called graphic approach. Okay. So convolution, we have given the definition in the previous lecture. So definition is basically very straightforward. If you have two causal signals, f of t and y and g of t, then the convolution is basically denoted by the following operation. We use a star here between the two signals to represent this is a convolution action, and the actual action is given by this integral at here. Okay, so if you look at the integral, it involves the multiplication of the original two time functions. Of course, now we're doing integrals, so we have a dummy variable tau. Integration is with respect to the tau, and the limit is go from 0 to t. Okay. You have a multiplication of f of tau times g of t minus tau. Okay. So that's basically what it appears to be, right? So we're going to have a better understanding of each one of these, how we can calculate this using graphic approach. But the bottom line that in the previous lecture we have concluded that when you look at the results of this convolution, right? So your end results of the convolution should be another time function. So that's basically firmly removed. It's not going to give, maybe it's a constant, but it's going to be a time function. So that's the results of a convolution. And another thing, the property of a convolution is that when you convolute f of t convolute g of t, it's the same as g of t convolute f of t. So this is a property what we call a commutative property. So you can change the order of the convolution. Okay, so now let's look at this graphic approach at here. So since we're starting, so I'm going to use an example, and also I'll try to go a little bit slow. Right? But of course, in the future, you don't have to write down all the details like what I'm doing right now. Okay, so let's consider the following f of t and g of t. So f of t equal to this is a function given for f of t, and g of t is given as 2. Okay, that's the two given time function, and we are going to calculate the convolution of f of t and g of t. Okay, so this is just the piecewise function I was referring to, and also you can clearly see that both of the functions here are causal function, because you can see here the first one, right? When t is less than 0, it's 0. And this is when t is less than 0 is also 0. So both are causal function. So first step, right? Graphic approach means we should graph out the two piecewise function. And that's something I mentioned in previous lectures, very basic function, not very complicated function. Like this is basic exponential decay function. This is also basic constants, right? So you need to be able to graph them out if the question, doesn't graph for you. So the first step, so graph f of t and g of t. So I'm just going to graph over here. And then this one over here. So this is exponential decay function. To graph this, let's say you set t equal to 0. Of course, you get a 1. And as t goes to infinite, this term goes to 0. So you get a graph looks like this. Okay. And this is your f of t. T. And then let's do the g of t is piecewise function when t is less than 1. So you put a 1 over here. Right? 0 when t is greater than 1. You are at 2. So it's more of what sometimes we call this kind of function, call it step function. It steps up and then maintain a constant value, right, from that time on. Good. So once you graph this out, right, and then let's look at how we do it, calculate the convolution using graphic approach. Second step, okay. Now, second step is you go back to basically the community property, because we know f of t convolute g of t is same as g of t convolute f of t. So when you do the computation, so technically, right, you could swap this notation. So instead of this is a convoluting this, it can be this convoluting this. So both should be the same results. Okay? So in other words, you essentially this step here, you determine what do you want to do. Do you want to do f of t convolute g of t, or g of t convolute f of t? So which one do you want to put it in the front? Now, most of the time, it doesn't make any difference at all. Okay, most of the time, but just sometimes, especially when it comes to the graphic approach, it might actually help you a little bit if you select the order a little more wisely. Okay, but that I don't have a definitive answer to say which one will be better. It's more of experience, right? Once you do this, and you might actually be able to notice. Okay. So let's say we are going to use this just traditional f of t convolute g of t. So now you go back to your formula. Okay. So since we're doing this, now this is the formula we're going to use: f of tau and g t minus tau and d tau. Okay. All right. So now to come to the third step now, more for the actual steps, okay, involving the graphic approach. So for this step here, you look at the formula. What's involved here, right? Inside the integrals, you have to find f of tau, and you have to find then g of t minus tau. Okay, you have to find these two terms first, and then you multiply these two terms together, and you do the integrals, right? So that's why what we're gonna do first. Let's find f of tau first. Okay, so let's see. Find f of tau. So how do I find f of tau? Well, that's pretty simple. All I need to do is what? Is to replace the t with tau, right? So that's all I need to do. Actually, there's not much to do. So all I need to do is change t to tau, meaning I'm still gonna graph that. Okay. So I'm still gonna graph this. And of course, now I'm graphing f of tau. So what has changed? Really nothing changed, right? So this graph is f of t. All you need to do is change the t to tau, and then the graph is remained the same. So of course, the current function or the current curve is represented by what? E to the power of -2 tau. That's all you need to do, right, for this step. Okay, so for this step, we got this graph right here. So that's under the same step here, okay, on the same step. So we find f of tau, and I say I need to find g of t minus tau. Okay. So then the next step is to find g of t minus tau. And my writing is not always very precise, just make sure this is t and this is tau. So before we I present the detailed steps at here, right? Let's think about how can I get g of t minus tau from where? From g of t. So this is the idea, right? You have been given g of t. Now you're looking for g of t minus tau. Okay, good. So here's the general thoughts here, right? So I'm gonna I have a g of t. Okay, then I'm going to obtain g of tau first. Very much like the steps we did for f of tau. So what do you do from this step to this step? So what you do is you basically change the t to tau. You get a function of tau. And once we get this, we will do a reflection. G of negative tau. So we've done this in the first tutorial. So when you have a function of tau, okay, you put a negative in front of tau, so that graph will be reflected about the vertical axis. Right. So once we've done this, and then we do this step. And from here to here, right, this is the step I find sometimes a little confusing to students. Okay. From these steps to step, it's confusing because I introduced back the t here, right? And the t at here is a variable, okay, first for. So that's where a lot of time we get confused. But if I don't use a t, let's say if I use a 1, okay? Yeah, and you probably will feel comfortable. You say, okay, so what's the difference between g of negative tau and g of negative tau minus 1? What is the difference? Shift to where? To the right by 1 unit, right? Yeah. However, what I don't need tau minus 1 here. What I need is t minus tau here, right? So I'm going to replace this with a t, okay? But you can still firmly think of a t as a certain quantity. It's just the quantity is going to be a variable quantity, okay? So then you can still see exactly the same thing, right? From here to here, you're shifting g of negative tau to the right by t amount of units. Sorry about the little writing here, right? So that's what happens for this step. And of course, if you move the negative into the bracket, and you can clearly see this is g of t minus tau, which is what we're looking for. Okay, yeah. So that's the step we're going to go through to find g of t minus tau. And of course, we're trying to find a graph of this g of t minus tau. So let's do that. So first is g of tau. So the many steps that are here, we do that. You try to do that, write it down at the beginning at this stage. But in the future, when you get more comfortable, you can certainly skip a few steps. Okay, so g of tau, according to the graph. Yeah. So for example, by meaning not skipping any steps for now, is that when you draw this graph right here, what I need you to draw the tau over here, right? Write it as a tau, because you don't write it as a tau, sometimes you think of this as a t. Right? You need to understand like what function you're plotting at it here. You're not plotting g of t, you're plotting g of tau. Right? And you also write the vertical axis clearly. This is g of tau, not g of t. So that's one of my expectation at this stage. When you plot it, you use a ruler, right? Make a better drawing than what I'm doing here, and label everything clearly. So next step, I'm drawing g of negative tau. So as I said, g of negative tau is just a reflection around the vertical axis. So reflecting this graph, mirror it right around the vertical axis. So you end up with a -1 here, and then going this way. That's g of negative tau. Okay. The next step is a critical step. We're drawing g of negative tau minus t, which of course give us g of t minus tau. So this is a critical step here. So for this step, as we mentioned, right, by looking at it, you're shifting this graph to the right by amount of a t. The only thing is we don't know the t yet, right? This is actually the next step. Okay. How much are we shifting? 1 or 2 or 3, right? That really depends, but we're shifting by amount of t. So shifting by amount of t, if you're not quite, your brain quite not working with the variable, you could think of, okay, I'm shifting this graph to the right, let's say by 2 units, right? So meaning, if I shifting to the right by unit, this -1 becomes what? 1, right? So what did you do? You -1 plus 2, isn't it? Right? So if I shift 3 units, the -1 plus 3. So now you can say, okay, if I shift by t amount of a unit, then this edge, where should be the edge? The actual location edge should be not 0. I'm shifting to the right by amount of a t. So where will be the location of the edge? Sorry, louder. T minus 1, right? Or -1 plus t, right? As we just did, you know, if shift by 2, you -1 plus 2. Shift by 3, -1 by 3. But I'm shifting by a general amount t. So it should be -1 plus t. So this graph here, but I don't know what a t is, right? So this is why I'm going to just arbitrarily draw the drawing at it here, and -1 plus t. Okay. So this step here, you know, it does require a little bit a customerization to what exactly the t is, right? Yeah. Okay. Of course, you might argue, so why do you draw this graph over here? I mean, if your t is, let's say 0.5, then -1 plus 0.5, your drawing is actually here, right? Yeah, which absolutely makes sense. But remember, what we're drawing at this step here is more of a general drawing. That's actually the next step we will differentiate based on the actual value of the t. Okay, good. So now once we do this, once we're here, we got both of the graph for this is 2 here. We got both of the graph for f of t and g of t minus tau. Okay, so here's what I'm going to do. The next step, which is number 4. Okay, so now number 4, we're going to do the integral now. Okay, so we'll get back to the integral because we find graphs of both f of tau and g of tau. So remember the integral, is 0 to t f of tau, g of t minus tau, and then d tau. Okay, this is your original integral. So I'm going to redraw the 2 graphs at here because the screen. So first, let's redraw f of tau. Then let's draw g of t minus tau. Okay. All right, so get back to the integral. What's involved in the integral here? The integrand is f of tau multiplied by g of t minus tau. This is the integrand. So the integrand essentially is a multiplication of the two functions, or in other words, you're multiplying the two graphs together, right? Yeah. So in the one of the lesson I mentioned manipulation of the graphs, addition or subtraction, right, or multiplication of the graphs. I mean, multiplication of graphs, addition or subtraction, there's no difference from just a simple computation of the two expressions. Okay. So for example, if I multiply the two graphs, how do I produce the results? So what I have to do is I find the value at this location and then find the value of this graph and then multiply by the value of this graph. Then I will get point of value for the multiplication of two graphs at this point tau, right? Same thing. And I have to find every possible values around this horizontal axis, multiply them all out, and then you produce the resulting multiplication. Okay. So now let's think about the multiplication, right? Okay. So for example, right, let's say if I multiply, if I'm looking at this range here, which is tau less than 0. Okay. So there's 0 multiplied by a non-zero, you get a zero value, isn't it, right? Yeah. So if you put a 0 value here, then that integral will be 0. Okay. Yeah. So this is sort of leads you to the graphic approach. You don't really care about the 0 part of the multiplication. You only care about the non-zero part of this multiplication. And how do you know that where I'm dealing with non-zero part, right? So you have to basically look at the graph at here. You can easily find out which part you have a non-zero and which part you have these 0 values. Okay. Yeah. So now let's think about this a little bit more here, right? So remember, this t right now is still a big uncertainty to us yet, right? It's not like you're moving 2 or 3 units to the right. So t is something you're moving. It's a time quantity at here. Okay. So I want you to think, see, if t is a 0.5, where is this shifting graph at here? It's over here, right? If t is negative, if t is 0.5. Okay. If t is 0.5, so suppose t is 0.5. So you have the graph over here, and you have a graph over here. Okay. Now, can anybody tell me what would be this integral? Yes. Yes, right? If I pick t equal to 0.5, you multiply the two graphs, the blue one and the red one here, and they don't overlap, right? And they don't overlap. When you multiply together, you get a 0. Okay. So basically, the f of tau and g of t minus tau you multiply will be 0. Right. So similarly, if I move a little bit more here, it could still be 0. So the non-zero only happens when what? When this edge is on which side of the vertical axis? On the left, on the right side of the vertical axis. So basically, it only happens, right, when you start to have, sorry, my drawing is not very accurate, but you know, it only happens when the edge at here is beyond the vertical axis on the right side. So I would say what right here is all observations. Okay, so there will be overlap when the edge here is -1 plus t, right? This is edge, is on the right side of tau equal to 0. A vertical axis. So this begs the question now. What makes the t value, right? What makes the t value so that this edge is on the right side of the vertical axis, right? Yes. Greater than 1, exactly, right? So based on what I'm writing at here, meaning the -1 plus t, right, has to be greater than 0. And that gives me t is greater than 1. So if you have amount of a t that is larger than 1, then this graph, this step graph here, will have a certain portion, right? A certain portion on the right side of the vertical axis. And that portion here, right, have overlap with your f of tau. Okay. That means when you multiply these two together, you won't have a 0 value. You will have a non-zero value. And that's to our interest at here. Right? So this is actually quite an important observation because you see, what we're doing is we're integrating basically this graph here, right? So the t value really determines, right? Really determines how this integral will be conducted. Okay. Yeah. Sorry, is there a question? Okay. 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 So I'm gonna erase this a little bit here just so that I have a better drawing at it here. Okay. So erase the green parts. Okay, so this blue one clearly is a case when t is greater than 1. Okay, so now let's get back to this case here. So now I'm considering t is greater than 1 now, right? This is t greater than 1 case. Maybe let me before consider this. So when t is less than 1, okay, when t is less than 1, the integral or the convolution and we have already concluded when t is less than 1, the convolution is what value? 0. Okay. And when t is greater than 1, and the convolution will not be 0 anymore. Okay. And we'll be interested in what is f of, so we'll be interested in what's the multiplication results of this f of tau times t of t minus tau. Okay. So get back to the graph right here. Okay. How do you multiply the graph, okay, of this kind of situation when t is greater than 1, right? So what do? Same thing, right? You can start from the left side and you start multiplying. Obviously, it's always 0 when this is less than 0. Okay. When what is less than 0? When tau is less than 0, because you're integrating, right? You're integrating over d tau. Okay, you're integrating with respect to the dummy variable tau at here. So you can see when tau is this range here, you got all 0, right? When you multiply the two things. When tau is greater than 0, so how are we going to multiply? We pick a point over here, then multiply by this point, which is 2. We pick a point over here, multiply by this, which is also 2. Okay, but every point you picked from this curve is e to the power negative 2 tau, right? E to the power negative 2 tau. So guess what? If I pick a point over here and then multiply by a point over here, what do I get now? 0. I get a 0 again, right? So the multiplication for non-zero multiplication results only happens within which range? When you multiply the two graphs together, sorry, cut louder. -1 plus t. Range. I'm looking for a range. You see, we're talking about the integral with respect to tau, right? So I'm looking at the range within which range this multiplication is non-zero. Yes, Bert. No, 0 to infinity, including this portion here, right? For this portion, this 0 multiplied by non-zero is still 0. Yes. Exactly, right? 0 to -1 plus t, right? From here to here. So this will make you feel a little better if I draw a vertical lines, okay, going straight up. There is overlap between 0 and -1 plus t. So because we're doing integral, remember, we're doing integral now. You know, you're doing integral about the tau, which is this axis out of here. And you only care about the non-zero portion, right, for this integral. And that's clearly only happens when both curves are overlapping with each other. And only happens in this case between 0 and -1 plus t. So even though your original integral limit is 0 to t, and that's your formula, okay? But in this case, guess what? You are not really integrating over the whole range 0 to t. You're only integrating from where to where? 0 to -1 plus t. Right, that's your integral limit for the tau edit here. Because that's the range you have non-zero value for the multiplication of the integrand. So let me write it in here. So only for a tau greater than 0, less than -1 plus t, f of a tau times g of t minus tau is non-zero. And that's how I end up with this new integral limits added here. Okay. So then within this range, 0 to -1 plus t, within this range, what is the value for f of a tau, right? Within this range, the value for f of a tau is this original function value. So you can now replace f of a tau with e to the power -2 tau. Within the range 0 to -1 plus t, what is the value of g of t minus tau based on this graph, which is 2. So times 2 d tau. That's it, right? Up to this stage. So remember what we're doing, we're still calculating the convolution. Right? So this is a convolution of this. So within this range here, you get this expression for the integral. I mean, up to this, I think everybody should be able to do this integral, right? This is just an exponential decay function. Of course, the limits is not a constant, but that's okay, right? So if you need, can put a 2 outside here. If you would need to brush upon this integral here, I mean, it probably does require a very simple substitution rule, right, in order to do this. I think in my lecture, in my review, I mentioned that what I'm going to do is, in my case, is I use a very simple substitution. I change the tau to -2 tau so that I have the same quantity as that, right? However, I'm not supposed to change the question, right? So d -2 tau should give me -2 d tau. So I'm basically adding an extra -2 at here, right? So I had to get rid of the -2 to maintain the same equality. So essentially you can divide -2, so then you're getting rid of this -2. So this way, I'm not really changing the question here, but now I have the same quantity, -2 tau, -2 tau. Okay. And we all know when you integrate e to the power of tau d tau, right, you get e to the power of tau. So basically, whatever, as long as these two quantities is the same quantity, right? Doesn't matter how long the quantity is, you get the same results, e to the power of that quantity. So then what do I get? So -1 under here, and then this is e to the power -2 2 tau for the integral, and then limit go from 0 to t minus 1. So tau go from t0 to t minus 1. Plug in the limits, and you get basically, you get this result: 1 minus e to the power of negative 2 t minus 1. Okay. So this negative 1 is just negative in front. Is that clear from here to here? Oh, I'll do that exercise to you. Okay. All right. So now you can summarize now. Okay, you can summarize. Essentially, you end up with 2 situations for the results of this convolution. So this f of t convolute g of t. First, it's 0 when t is less than 1. And when t is greater than 1, you have this one here. So technically stop here. You don't have to continue anymore. But of course, if you're interested, you could graph this out just to take a look at what is this piecewise function, right? How does it look like? Okay. Again, this is exponential function. As t go to 0, you end up with 0. So you basically, the whole function will end up with 1. And I actually start from 1 at here. So it will go up, but it will approach 1, okay, infinitely. It will not touch 1, but it will approach 1 infinitely. So that's what this graph will look like. Cool. Yeah. Now, if I have to use a very simple concept that you probably have accepted unanimously in the past, when you do the integral, right? We all understand the results of the integral give you is the area of the integrand, right? Underneath the integrand. Okay. So in this case here, the integrand is the multiplication of 2 functions. So then you could also see that what you get over here, right? What you get here is the area under f of tau times g of t minus tau, okay, with respect to the t, at the t, because there's a different t value. You get this value, okay, yeah. You get basically still area concept. Any questions? Okay, so this is a very detailed steps, right, showing graphic approach to solve this convolution. But I think I still want to go back to this question a little bit here, okay? Yeah. Okay, so it's this step, I think I need a little bit more comments. So t greater than 1, greater than or equal to 1. In this question, right, I have only identified this one range t greater and equal to 1, which is multiplication of the 2 graph, and the integral limit is 0 to -1 plus t. Okay, yeah. So in other words, you think about it, right? You might think is, could it be possible I can further divide the t's range, okay, maybe t from 1 to 2, and then 2 to something else. So in other words, will the overlap between this graph produce different range of integral limits? So this is actually, I'm going to demonstrate in the next example about what I just said here, okay? So you look at the current overlap, right? And the current t range. You think about the overlap at 1 or 2 or 3 or 4 or 5, any number, okay? Any number. So it doesn't matter what number, right? So this graph will always look like this, or this graph will always look like this, but it's always -1 plus t. And the overlap always what? Always between 0 and -1 plus t. And it's always this function e to the power -2 tau multiplied by this value 2 in this question. Okay, so that's why here you see beyond t greater than 1, I don't have any actually further complications. All right, so that's what this example is actually showing us. Right, but next example will be a little bit more complicated. Okay, and requires you to be a little more vigilant, you know, when you try to use this graphic approach. So let's consider this graphic here now. All right, so let's say I have a two function g of t, f of t, which are two boxes. Two boxes here. I'm convoluting the two boxes and see what that produces. I'm going to follow the graphic approach. Okay. First step, so I'm going to skip a few writing in here. First step, you determine, are you doing f of t convolute g of t, or are you g of t convoluting f of t, right? So anyway, so I'm going to do g of t convolute f of t convolutes f of t as my order. I'm going to change. Then, so that's your first step. And then the second step, graphical approach means I need to find f of tau first. The graph didn't really change at all, except the horizontal axis become tau, right? Yeah. And then I need to find a g of tau okay. Then flip it. G of negative tau, flip it, you get this g of negative tau. And now next step, shift it. So g of negative tau to g of negative tau minus t. So this step is a critical step. You had to plot it very precisely, right? Yeah. Precisely, also label it precisely. All right, so we're shifting this graph, this box. We're shifting this box to the right, in this case, right, to the right by a t amount. Okay. So now when you shift, you have two edges at here, and you have two edges for the box. So this edge goes to the right by t amount of a unit. The coordinates of this edge becomes t. And this edge goes to the right by t amount. And the coordinate of this edge becomes t minus 1. Or you could keep it as this, right? So just to be consistent, you're shifting to the right by amount of t. So this is your g of t minus tau. Good. Once you are here, then you're ready to calculate, right? The next step here. You're ready to calculate the multiplication of the two curves or two graphs. Okay. So when you do this step of multiplication, right? And this is where you have to examine, okay, examine how am I going to shift this graph right here, okay? Or how much am I shifting? And how much of the shifting is affecting the multiplication of these two graphs, okay? So for example, this graph is always here, right? And I don't know what the t-values yet, right? So let's see if, I'm just writing scribble here. If t is less than 0, and so you're shifting this graph by a negative value. So negative value means instead of shifting to the right, this graph actually goes to the left, right? So if this graph goes to the left, then you have a box basically over here, right? And then you're multiplying the two graphs. You multiply this graph with whatever results you plotted it here. So you can visualize if t is less than 0, you multiply this graph with this box with a box over here. So guess what? You will end up with a what value? 0, right? So that's what I need you to at this step, right? In your head, graphical vision. That's what happens when you're shifting value t is less than 0. Okay. So if t is greater than 0, that's the drawing looks like this, right? And you will have non-zero overlap portion. However, this is where things get a little complicated. When t is greater than 0, my box could be in this position. My box could also be in this position, right? So then you can clearly see the overlap between this original f of tau and this g of t minus tau has a very important relative relationship. For example, if my drawing over here, okay, if my box is over here, and then clearly this box and this box, they don't overlap. If they don't overlap, then the multiplication will be 0. So that question basically is what gives you this case, right? And how much t are you shifting to make these two boxes are not overlapping each other? So this is essentially the point I'm making. Now you have a little bit more complicated, different so-called patterns of overlap based on the actual amount of t you are shifting at here. Okay, so that's why I need to be a little bit more careful for the values when t is greater than 0. But let's put this down. If t is less than 0, okay, and you get f of t convolute g of t equal to 0. And that's pretty obvious. And then I'm gonna just specifically talk about when t is greater than 0. Okay. So, and now I'm going to present a few more patterns now. Okay. So first of all, I'm going to draw the first pattern. Okay. The first pattern is this box goes across both sides of this axis. Okay. It goes across both sides of vertical axis, which is tau equal to 0. For this pattern here, so just for your reference, let's put the f of tau on top of this. So f of tau, use a green color. Here's f of tau. Okay. Yeah. So now you can see where is overlapping happening. Is from where to where? For which range of tau the overlap is happening? Exactly, right? That's where overlapping is happening. Okay. Now, but before we write this down in here, let's again think about this the drawing in here. The box is in this location. Then the question basically is, at what value of the t you actually have this current drawing location for the red one? right? So -1 plus t is on the left side of the axis, and t is on the right side of the axis. So basically, if I impose a condition, -1 plus t is less than 0, and then t is greater than 0. So actually, you could put an equal sign, it's fine. Okay. If I impose this condition, then I'm guaranteed that this box is in this sort of a situation, right? And what does this constraint give us? First one give us t less than 1, right? The second one give us t greater than 0. So this give us t is greater than 0 and less than 1. So you can clearly see if I shift this box, right? Shift my shift this box. If I shift this box to the right amount of a t, as long as t is within 0 and 1, I'm guaranteed that this box is more or less in this kind of configuration. So I call this is a pattern. Okay, so let's say I call this as a pattern number 1. This is a pattern, and this under this range of t, the integral, right? The integral only is meaningful between 0 and t. So the integral here is only meaningful between 0 and t. So you see there are two things going on, right? One thing is how much t you are shifting. And then based on that amount of t, what's the implication to the integral limit tau? So these two things always connected, right? So I'm going to stop over here and then I'll finish this example in the next lecture. Any questions, feel free to come forward. Yeah.
Why did we say -1 plus t smaller than 0?
You mean this one here? You mean this one? Yeah, this one?
-1 plus t smaller than like the last one.
Oh, this one?
Yeah.
Oh, this one?
Yes.
Well, I'm trying to make sure that this box here, which is g of t minus tau, overlap both sides of these coordinates. You know what I'm saying, right?
Yeah.
So then that means this edge here has to be less than 0. And this edge here has to be greater than 0. So that's what these two conditions, what they are for.
Yeah, but when t equals 2, then there will be overlapping with the f of tau and g t minus tau.
Come over here. Come in here. Come in. And then what?
So then we said like t, let's say equals 2.
Mhm.
So we said that like